Hello everybody. Let us start our discussion today. Today we will discuss about a topic called photometry. So let us start by asking the question that what is photometry? Photometry is measuring amount of light falls in. Can be in some wavelength regions. Okay. Photo means light and metry means measurement. Now, today we'll talk about photometry of a very particular type of object which we call the point sources. Okay. So imagine that there is a point source. Luminosity of this is, or let me write luminosity, not specific luminosity for the time being. The luminosity is L. So flux of that source at Earth is L by 4 pi d square. This will all work out if you want to do it for specific flux or specific luminosity, so which I am not putting in because that's not required for this particular discussion right now. So this is, the source is at a distance d. So this is the flux. And what do I mean by how do I write a point source, or how do I describe a point source? Intensity. When we say point, it essentially means that all the intensity comes from a certain direction in the sky. And remember that we are dealing with, we defined what is this theta. So we are looking at the small portion in the sky, and from the center I can just imagine this part of the sky which is a part of a hemisphere as a flat surface, because we have taken a very small part of that hemisphere, and east west I call theta x and north south I call theta y. So that theta vector is any vector given in this coordinate system. So what will this be? It will be this flux, and all the intensity for a exact point source will come from a given direction, say theta 0. So if the point source is at theta 0, say this is the point source. So this I should be able to write this way. Remember that the Dirac delta function, it's a 2D Dirac delta function here, it has a dimension of 1 by angle, or 1 by solid angle. So flux per solid angle is the intensity, which is nice. However, when I observe, so this is the flux, the observed intensity is actually not this, because when I observe, the effect of observation is a convolution of the intensity function in the sky with the beam of the telescope. So I have to calculate it this way. So this will then turn out to be f times the beam itself, because you know that is the property of the integration with a delta function. Hence, for such a source, which is a point source, if I integrate over I0 theta d theta, that is essentially f is the flux of the source, it doesn't depend on theta. And by definition, the beam is constant, is integrated to 1, so this is equals f. So I can get the flux of the point source, just integrating over the beam. Now, in reality, obviously, I don't have a continuous function which we have measured. Remember, we have measured the values of I0 in case of optical astronomy in different pixels, right? So let me show you a picture which will make this point more clear. Let's first look at the figure in the left. There are the squares defined by the grid lines. Each of those are 1 pixel, and you may measure the intensity in each of those pixels. What is shown here in the color scale is the beam. So where you have the brighter spots, you have more transmission through your telescope, so the beam has higher value. Where you have darker parts at the corner of this picture, so you have lower values. Within the beam, we need at least 2 pixels. We have more than 2 pixels here, which is very nice. The circle here corresponds to a contour of an observed source. So I have a source which I have observed using these pixels, and what I get is that certain value, say 0.1, corresponds to this line. As you see, the source looks also like circular, and the beam is also circular. This is because this source is not resolved by this telescope. So any source which is not resolved by the telescope will appear like of the shape of the beam, just like here. On the other hand, if I look at the second picture, I have a source which does not look quite like the beam. It is an extended one. So today's discussion mainly will talk about only the point sources. In radio astronomy, usual unit chosen for I is the flux unit, which is Jansky, per beam. This is because given the telescope, the beam remains fixed. Different users can choose different grid sizes, different size of those pixels. So they will get different fluxes if it is defined per unit pixel. Instead, we define it per unit beam such that whatever pixel size you choose, the value of the intensity at each pixel remains the same. In optical astronomy, remember that the beam width can be written in units of either arcsecond square or steradian. So this has the Jansky per steradian, which is the actual unit of I. In optical astronomy, one chooses the unit for I as arg per wavelength per meter square, and then usually per arcsecond square. There are differences. There is not a very standard of the units, but this is usually what one chooses. Okay, so now let us ask the question. So we'll look at now point sources, and we understand what we mean by a point source now. So we look at a very specific type of point sources. We call them stars. Okay, and these stars has a certain luminosity L and a specific luminosity L, and let me write in terms of lambda because today's discussions will be mostly in terms of the wavelength instead of the frequency. So if you know what is in terms of frequency, you can also get L in terms of lambda, so that's not a big deal. When people assigned certain numbers to different stars in the sky, there was only one instrument which could measure these numbers, or relative numbers rather, and that instrument was our eye. And our eye, so the scale of the brightness of the star, and you see that the brightness is now will be, because it's a point source, it will be completely dependent on the flux of the star at our eye. That scale was determined. Our eye and all other instruments are sensitive to intensity in logarithmic scale. That gives us a huge range of sensitivity. Like if it is in logarithmic scale, our ear can hear frequencies from 20 hertz to 20 kilohertz. If it was in linear scale, we could not have heard so much range of frequencies. So the way the flux was introduced is by a quantity called magnitude, and it was done by Hipparchus. It's written usually with a small m. So it's in log scale, log to the base 10 of flux plus some constant. So this constant, basically, you can only, by eye, you can only do this with respect to something. So this is defined by the reference stars. So you consider a star and ask the question and say that this star I will consider standard magnitude 0, and then with respect to that, if something is brighter, it will be some magnitude. If something is less brighter, it will be some other magnitude. Now, this m can be either for integrated over all wavelengths, so then we call it a volumetric, or it can be in a given lambda. So that is more like specific. Alpha determines the scale. So just like if I give you a ruler, the scale there is centimeter. So alpha determines how much different we call. So if I say magnitude 1 and magnitude 2, how much is the difference between these two? Now, this entire definition has nothing to do with any physics apart from the fact that we observe in logarithms. Our eye is sensitive to logarithm of flux. But everything else in this definition is just by choice. C was chosen, the star for which this C was fixed, the magnitude was fixed to 0, is the star Vega. And alpha was chosen to be minus 2.5. The consequence of that is that if you have anything brighter magnitude, it will have a lower, anything you have brighter flux, it will have a lower magnitude. So this means bright implies low m. For example, if we talk about sun, it has a magnitude of 26.74. If I talk about Sirius, which is the brightest star in the sky, it has a magnitude of 14.6 or minus. Now, let me also tell you that these numbers are not, this is alpha 1, 2.5 is kind of fixed, but what is the value of C is not always Vega is taken to be absolute 0, because it depends on different telescopes. Now, why would it depend on different telescopes? Because you see, just like I may have defined a volumetric magnitude here, I can define a magnitude which I call m lambda. What will be now m lambda? M lambda will be minus 2.5 flux at that lambda plus some 0 point at lambda. And now this lambda is a certain wavelength region. It's not a single wavelength again, it's a wavelength region, and that wavelength region is selected by putting a physical filter, a colored glass in the optical path of the telescope. And depending on the property of that colored glass, I have to change the definition of C lambda. Okay, so it's not fixed, because if you go to different places in different observatories, they will obviously use different filters, different physical filters, and that will give rise to different definitions of the magnitude. So that is all right, because every place what magnitude they are using, they will tell you, and then you can convert that to get to the flux. Because everybody tells what is C lambda, m lambda is something you will measure, you can get to what is f lambda. Okay, now let us talk more about the specific things. So remember that now I can also write m lambda in terms of the luminosity of the star. So the luminosity, specific luminosity, if it is L lambda, so this is this by 4 pi d square plus C lambda. Maybe that we are looking at a cluster of stars. So there are a few stars there, and we are looking at their collective properties. So we are looking at a cluster of stars from the Earth. Now the distance between the cluster and the Earth, which is d, is usually much greater than the distance of the individual stars in the cluster. So I can ignore that. So if I ignore that, then for a cluster, I will have m lambda 1 as minus 2.5 L lambda 1 by 4 pi d square plus C lambda, and if I have m lambda 2, that will be again minus 2.5 L lambda 2, because the two stars can have different luminosities, but they are almost at the same distance away, and I'm looking at the same wavelength, so C lambda is same. So you see that the difference in the magnitude directly tells you about the ratio of the luminosity. I forgot to put in log everywhere. There is a log to the base 10 here. There is a log to the base 10 here. So minus 2.5 log to the base 10. This is just the ratio of the luminosities, which is very nice, because then for the cluster I can find out the ratio of the luminosity of all the objects in the cluster. Now, as you see already here, m lambda depends on not only the luminosity of the source, but also the distance to the source, d square. So m lambda depends both and d. So this is called apparent magnitude. So we defined an absolute magnitude for the stars, which I call with capital M. This is nothing but the apparent magnitude of the star if the star is at 10 parsec away. Now, from the quiz that you had, you have seen that 1 parsec is 3.0 0.0568 into 10 to the 16 meter. Is an astronomical unit. You should look at how this unit is defined, why this unit is this much of meter. So this absolute magnitude gives you a direct estimate of the luminosity of the star. Or if I subtract the absolute magnitude, if I subtract the apparent magnitude from the absolute magnitude, the C's goes away. What I will be left with is minus 2.5 log 10 of, in one case I have L lambda by 10 parsec square. 4 pi I am not writing, we know that it will cancel out. In the other case I have the same L lambda, but now the distance to the star square. So you see that this gives me minus 5, because the square in the distance will come out and it will multiply by 2.5 and give me 5, and then 10 d by 10 parsec. So distance in unit of 10 parsec. Or I can invert this relation. So this was m minus m is this. I can invert this relation to get the distance, which is in unit of parsec, is 10 into 10 to the power minus m by 5. So if we know from some independent measurement, if we already know capital M, we can know the distance to the star. Okay, now there are objects which has known luminosity, and if you know the luminosity of the object, obviously you will be able to figure out its absolute magnitude. So they have known absolute magnitude, then you can figure out their distance. These objects are called standard candles, and this way, because we can measure the distance, m minus m is called the distance modulus. And when we will discuss cosmology, you will see that this has an immense importance in cosmology. Now, how do I get the volumetric magnitude? Well, when I get the volumetric magnitude, if I want to get the volumetric magnitude, so let's say volumetric magnitude. So volumetric apparent magnitude will be minus 2.5. Now I don't forget log 10, 4 pi d square here, and this will be the flux integrated over all lambda. So if I somehow know the distance, usually, let me tell you what is done usually. We talked about this clusters of stars, and it turns out that somehow you may know about the distance to one of the stars in this cluster. So if I know one of the stars to the distance to one of the stars to the cluster, the other stars are not very far away from that star, so we approximately know the distance to all the stars in the cluster. So once I know the distance to all the stars in the cluster, I can figure out the apparent magnitude. From the apparent magnitude, I can figure out the volumetric magnitude, the absolute magnitude of the stars. And if I know the absolute magnitude, I can figure out the flux. And if I know the flux, I can figure out the luminosity. I'm sorry, this should not be flux, this should be the luminosity. So let me correct that. So this should be the luminosity, because I am getting flux after dividing by 4 pi d square. Now, here is an important information for you. Stars radiate almost like a black body. So what will be the luminosity for such a black body? The luminosity of the black body, as we know from Stephan-Boltzmann's law, is 4 pi r square. R is the radius of the star, T of the star to the power 4, and then Boltzmann constant. And I said that it radiates almost like a black body, so it's not quite like a black body. There are some emission and absorption lines, and it deviates a little bit from the black body curve. So we define, this is the luminosity of the star, and again this is a definition of a different type of temperature now. So we define effective temperature of the star this way. So this is effective temperature. So what is the effective temperature? If somebody gives me what is the luminosity of the star and the radius of the star, I can put that in this formula and get the effective temperature. Okay, so this definition, you can, if you wish, you can also write this way. Same thing. Okay. What practically done is that, okay, it is almost like a black body, which means to some approximation I can take the effective temperature as the black body temperature of the star. And in that case, if we can independently measure T effective and LB, we'll know the radius of the star. So we'll see that knowing the radius will be very important for us. And we also have seen most of the stars are like point sources, which means we do not resolve them. We do not see them as extended objects. We cannot figure out their radius, though it can be done using certain methods for some of the nearby stars, but in general it cannot be done. So this, if I can figure out L effective and LB independently, then I should be able to figure out what is the radius of the star. For this, there are two methods. One method is what we will discuss here in this course. It is called, now this has a lot more advanced version, but I am talking about the basic methods again. So it's called Uvb photometry. As I said, to detect magnitude of different wavelength, you need to use a certain filter. So here, three types of filters are used. Now, these are not the only three types of filters which are possible. There are many different types, and even in this wavelength range, as I said, that different observatories use different filters, different glasses which gives you different filters. I am just taking some example here. Okay. So every wavelength will be written in nanometers. The first is ultraviolet. So I just write UV here. 365 nanometer is the passband of the filter. We'll see what it means. And 68 is the width. Then B, this is blue, 440 and 98. So it essentially, these means that it passes the light which has 365 nanometer mostly, and it also passes a little bit around 365 nanometer. That around is defined by 68 nanometer. V is not violet but yellow, visible, and this is 550 nanometer and 89 for the width. So the flux that will receive any wavelength will be given by, so flux, now this is the flux at a given wavelength or given filter. And R is the response of that filter. So we'll see what is a response. It basically tells you at different wavelengths how much is the transmission through the filter. So if R is more, you get that wavelength light more. That's all. Okay, and we can define m lambda, which is the magnitude of that at that filter, as log 10 f lambda plus c lambda. Okay, so before we go to further discussion, let us try to understand what does this filter do. So here is a plot of the blackbody curve. The blackbody is at 6000 Kelvin temperature. X-axis is in wavelength, and the y-axis are in arbitrary units. Dark black line is the blackbody curve. The response function R for these three filters are shown. So if I consider one of the filters, what the response function show you is the wavelength for which it will pass the light. For example, if I consider the U, there will be no light from 1000 nanometer passing through it. There will be a little bit for 400 nanometer. Mostly it will be at some 360 nanometer. So what I have to do to get the flux at that filter is multiply the filter response with the blackbody curve. That will give me the flux at that filter. One interesting thing which we can notice from here directly is that if I have the U filter and the B filter, the flux in this for this particular blackbody of the U filter will be less compared to that of the blue filter, because the blackbody curve start peaking there. Flux for the B and V may be almost same, V may be a little bit less. Okay, so just keep that in mind. Now, what we can do is the following. We can measure the total flux coming from that star. That will give me the total flux. We can measure the flux at two different wavelengths, and we know that for a given blackbody, the flux at two different wavelengths, the ratio of the flux is always constant. and that constant depends on the temperature of the black body. So if I measure the flux at two different wavelengths, I can get the temperature of the black body. So apparently what I can do is the following. Apparently, if we look at a star, we can measure the volumetric flux, or we can measure MV, the V band magnitude, and then if I know the V band magnitude, I know for a given black body, given the flux in the V band, what will be the total flux, and get the total flux, get the volumetric magnitude or flux is same, right? So even there is a name for this. So if I have M volumetric and if I have MV, the difference of this is called V band excess. Volumetric excess. Alright, so what I do is I measure MV, I add epsilon V to it, I get the volumetric flux, and once I know the volumetric flux and I know the distance to the star, remember that I measured distance to one of the star in the cluster, I can figure out the luminosity of that star. Next, what I can do is, from the ratio of the magnitude in any two bands, will directly give me the temperature, because you can check the ratio of the magnitude at any two bands will depend on the temperature for a black body case. Alright, but this we cannot do but there is dust. Remember that in the first day when I was showing you those pretty picture, in one case I mentioned that the star's lights are not seen because when the starlight passes through the interstellar medium before reaching our telescope, it also passes through dust. And what dust do is that it does absorption of this starlight. So if I consider the intensity that I receive as I lambda, this is I0 lambda of the star at that intensity, e to the minus tau of the dust. So if you calculate the magnitude, now remember that this will be, I can write this in terms of F also, flux in case of the point source. We are dealing with point sources now only, because for the point sources we can measure the intensity tells me the flux. So if I'm calculating this, say the V band magnitude, I will get minus 2.5 log 10 of F lambda. Now F lambda I can write F0 lambda. F0 lambda is the one which, F0 lambda is the flux which I would have got if there was no dust, right? And then e to the minus tau dust plus some CV. So let us write it in this separate forms. So log of A into B I can write as log of A plus B. So I get first this, and then I get minus 2.5 log 10 to the base E times, this becomes plus because I will get minus tau dust here. So this, I get this. So MV, you see, the observed MV, this is the MV that you would have observed if there was no dust. So let's call that MV0 plus this quantity. This thing is 1.086, you can calculate. So this entire thing is called AV. So AV is 1.086, 2.5 log 10 to the log e to the base 10 is 1.086 times dust, tau dust. So this has a name, it's called extinction. By the way, the same dust extinction happens because our atmosphere, and for optical astronomy observation, you actually have to correct for that. I did not talk about it in our lectures, but just keep it in mind. Now this I called for the V band. Now it turns out that this extinction depends on the frequencies or the wavelengths, because tau depends on the wavelength. So this depends on the wavelength. So that's why the suffix V is there. So when I measure the apparent magnitude in the U band, it will be like this plus AU. When I measure it in the blue band, and when I measure it in the visible or the yellow band, right? And it turns out that AU is greater than AB and AB is greater than AV. Remember that this A's are essentially optical depth times 1.086, which is just a constant number. And the optical depth is that of the dust. So if I know the property of the dust, I have very good idea about how the optical depth changes as a function of wavelengths. And that is what you are putting in here. Now let me define something for you. This is astronomical definition of colors. This is completely astronomical definition of colors. And it is completely unlike what we call it as color. So we have U minus B color, which is nothing but MU minus MB. Now, one thing to notice about the colors is that when I do U minus B, when I do MU minus MB, and let's forget about the dust for a little while, so I am doing for no dust case. What is MU? MU is some minus 2.5 log 10 of FU by 4 pi d square. And then I have minus of minus, which is plus log 10 of FB by 4 pi d square. Again, same star, d is same. Right? So which means because it doesn't depend on d, you can check, it is very easy to see from here that this is also same as the difference in the absolute magnitude. So this is an intrinsic property of the star. So this doesn't depend on the distance to the star. Okay, so you see that we are trying to get to that intrinsic property because this also depends on the ratio. So now we can see that if I bring the two logs together, so it will be FU by FB, and FU by FB will depend on the temperature. That is what we are trying to go to. But unfortunately, when I do U minus B color, which is defined this way, which is alright, but when I do U minus B in the observed case, it is Mu minus Mb, which is the original U minus B color, and then I have Au minus Ab. This again have a name. It's written in short form like this way, Eu minus B. And you see again, these quantities Au minus Ab will depend on the dust. It will not depend on the distance to the object, because again for there also, see what are the Au and Ab? So they are tau, and remember tau is, just to remind you, tau is integral of alpha ds, and that ds integral is in there, both of them, so the distance to the object will almost cancel out. So you see U minus B as observed is U minus B as actual plus this excess, it's called the color excess. And similarly, just like U minus B, I have another color defined which is called B minus V, which is B minus V 0 plus the excess B minus V color. So B minus V excess will be AB minus AV. And just remember that AB minus AV will be greater than 0 and AU minus AV will be greater than 0. In most of the cases, okay, there are regions where it is not true, but this is the basic. Okay, so let me show you what is known about these quantities. So from the study of the dust, these things are very well known. AV by E B minus V, this is of the order of 3. It's around 3.1. And E U minus B by E B minus V is of the order of 2. Okay, so these are all properties of the dust. Okay, so let me show you how these two things behave as a function of wavelength that is very well calibrated, and then you can figure out what is that for the filter that you are using, which is the visible filter in this case. Bumps in the bottom where you have written M, L, K, H, etc. These are the filters, and the filters that you are using is V, B and U. Those are also shown here. They look a little different than what you have plotted. The wavelength is in the top axis, and the curve here is A lambda, the extinction in wavelength lambda, divided by the color excess B minus V. And because we like to know what is the value of this, where lambda corresponds to the visible, so if you look at this curve, you will see this number for the visible band, which is given by V here. This gives you the ratio of E lambda minus V, which is that some lambda with respect to some lambda, what is the color excess of V band, with B minus V. And in this case, if we consider the wavelength of the ultraviolet radiation, you can figure out that the number will come out to be 2. Okay, so keep this in mind because we will be using this. Now let us see what will happen to the stars in presence of dust. So let me draw a cartoon picture here. This is called a color diagram, because in x-axis and y-axis both, we plot certain color. So in x-axis b minus v, in y-axis u minus b. And there is one thing to notice here, so I am just giving for you some pointers. B minus V increases this way. On the other hand, U minus V increases this way. It's a little odd. We'll see something more odd will come in later, but this is what it is. And one can figure out clearly, completely, that if the, so this is for black body. So if the star is radiating as black body, then one can easily figure out what are these values, u minus b0 and b minus b0, and plot those. That will give you a line like this. It actually have a so this, let me show you the actual line, which the temperature range for this is even more. I'm just looking at, say, this part of the line, and the temperature varies along this line. So temperature is a parameter which gives you this line. This is the line where, this is the line for the color of the star will lie if the star is radiating like a black body. What happens if the star is not radiating like a black body? So there is, star is radiating like a black body still, but there is dust extinction. And what does the dust do? You see, for the dust will increase E and increase both the color excess, because extinction in U is more than V and extinction is B is more than V. So as both of them increases, the color excess increases, so I have to add something to both of this. So what it will do is, if this is the star that I am trying to look at, it will go down a little bit, because then how it increases, and it will go towards the right also, and usually it moves more to the right, so it will land up here. So this is the position of the star after it has suffered reddening. So I put it by red. Okay, we can figure it out where it will move, because we said that this ratio we saw from the plot is about 2. So it will move with a slope of 2. This is essentially telling you this excess is, this difference is the color excess B minus V, and this difference is the color excess E U minus V. Okay, so you find the star here. So that is what you observe. You find the star here. What do you do now? So we find the star at this point. Now I have to correct for the dust. What do? I use the slope of 2 which is coming from here to move the point the red point to here. So this is that I move with a slope of 2. Okay, so once I do that, read the shift in the x-axis. This gives me E B minus V. Now I also know this. AV is then 3 times EB minus V. So I get the extinction in the visible band for the star. Now once I know the extinction, then it is straightforward, because if I know the extinction, I have measured MV, I can know MV0. So I calculate MV0 as MV minus extinction. And I can calculate the volumetric magnitude now, which is MV0 for plus volumetric correction. At V band. This gives me temperature. Okay, so I got the temperature. I'm sorry, this doesn't give me temperature. I'm extremely sorry. This gives me the volumetric magnitude will give me the luminosity. Okay. And the last thing now to do is that, remember that if I knew the ratio of the magnitude at ratio of the flux at two different wavelengths, I will get the temperature. Now I know the ratio of the flux at two different wavelengths because this is what I have measured, and we have read this EB minus V from the chart. So B minus V0, what is B minus V0 is this value. This I can now, from B minus V magnitude minus the excess. And once so this essentially is proportional to the flux at B band by the flux at V band, which is proportional to the luminosity at B band by luminosity at V band. This gives me the effective temperature. Okay, so this is how I can measure the luminosity and the effective temperature of these objects, which I call the stars. So let me stop there, because this is the measurement that will be very crucial for us, and we'll start using it from the next class. Thank you.